Welcome to another week of vector calculus. What I'm going to talk about today are gradient vectors and tangent planes. We have already talked about how to find a partial derivative with respect to x, or with respect to y, or with respect to any other variable. But it turns out because of that, there isn't a derivative by saying the partial derivative. What we'd much rather do is find the derivative, like we did in Calc 1 where you just found the derivative. It turns out that the gradient vector is going to be exactly what we need to talk about the derivative. But it won't give us a number, it will give us a vector. And that's why we call it the gradient vector. So we're going to start out to introduce you to this idea of the gradient vector. We'll talk about the directional derivative. And that's kind of the idea of saying instead of going in the direction of x, so on a map, that would be going due east. Or instead of going in the direction of y, that would be going due north. Maybe you want to go northwest or northeast or some other direction. So that is the directional derivative. It tells us how to find the derivative of a multivariable function in the direction of a vector. So after that, we'll get into the big thing of the day, and that is the gradient vector. So we'll look at using the gradient vector to find the directional derivative. We'll define the gradient vector in two different ways. One we'll define graphically, and also we'll define it more algebraically or with proper calculus. Then we'll look at the gradient vector's properties and things you can do with the gradient vector. We'll have a nice little application. Then after that, we'll get into tangent planes. So we have seen in first quarter calculus, or Calc 1, that if you have a curve, then the big thing in calculus is what is the derivative at a point. And that derivative helps you find the slope of the tangent line. Well, it turns out if you want a tangent plane, then we can kind of think as the derivative talking about not the slope of a plane, because that's not what we talk about, but the normal vector to the plane. And that's the day as we go. So hopefully you'll enjoy this lecture. So let's start out with the directional derivative. So I'm looking right now at this hiker. And you can think about the hiker has put his foot down. And that hiker has lots of choices. That hiker can go up or down or left or right in any direction he wants to go. And if he goes in, say, towards the left, then he's going to be walking upwards. He'll walk up the hill. If he goes to the right, he'll probably be walking downward. So we want to look and say, if you pick a direction, not just will he be going up or will he be going down, but by how much. So in other words, if he takes one little step in one unit in the direction of a unit vector, how much will he be rising or dropping in elevation? And that's what the directional derivative will talk about. So in particular, the directional derivative of a function z equals f of xy in the direction v, where v is some vector, that directional derivative measures how steep the surface is. And not just how steep upwards, but how steep downwards also. So is it going up, is it going down, and by how much in that particular direction? So how does z change when moving along v? And as we've seen before, when you have a function of two variables, it doesn't necessarily mean up or down in position. Sometimes a function might talk about temperature. And then we want to say how much hotter is it getting if you go in this direction or that direction. Or maybe it is electric field strength. And that's how much is the electric field strength changing in one direction or another. It could be all kinds of different things, but it talks about how much the dependent variable is changing if we move in a particular direction. So this picture shows several level curves to a function, f of x, y, z, of two variables, and a point right here that's marked. And the question is, what are the directional derivatives in several directions? So let's start out with the direction of the vector u, which is equal to 1, 0. So that direction is due right or due east, depending on how you want to look at it. So the question is, what is the directional derivative at that point in the direction of 1, 0? So what we can think about is if you take one step in that direction, how much is the function changing? So the way you figure that out is we draw a little vector in that direction of unit 1, and we say that if you move from the dot to the end of the vector, how much has the function changed? Well, we can see we're starting at the level curve 10, and we're going towards the level curve 15, but not all the way. It looks like it's about 3 in change in the f, or the function. So what we could say is the directional derivative of this function in the direction of u equals 1, 0 is about equal to 3. Let's look at another direction. Let's suppose that u is equal to 0, -1. So now we're going to take one step due south. And we want to find out how much is a function changing if you take one step due south. So here we're going from 10 towards the number 5. And it looks like we've gone most of the way, but not all the way. So it looks like we've gone about 3 downwards in the function. So we can say that the directional derivative of this function in the direction of u equals 0, -1 is about equal to -3. Let's look at one more example. Let's suppose now we have the direction of the vector 1, 1. So I'm going to draw a vector of length 1, and I want to see how much has the function changed if you move in that direction. So now, instead of going due south or due east, now it looks like we're going northeast. And if you go northeast, then it looks like you're going now from this level curve 10 up to about 15. So now the directional derivative in the direction of 1, 1 of the function f is about 5. So hopefully this gives you an idea graphically what it means to talk about the directional derivative. Again, these are just approximations, which is what you do with graphs, but for a lot of the time that's good enough. But now let's find out what is the gradient vector, because that's going to help us a lot about the directional derivative, and it'll do a whole lot more for us. And it's the following. So we have already had partial derivatives of a function with respect to x and y. So what the gradient vector does is it creates a vector that lists those partial derivatives. So in particular, let's suppose that f of xy is a differentiable function. Then the gradient of f, we often write this upside down triangle to represent gradient of f, is equal to the vector del f over del x, comma del f over del y. You can also write it in physics notation, which would be del f over del xi plus del f over del yj. In math, sometimes we use pointy brackets, a little less writing. We can also say that the directional derivative in the direction of a unit vector u of a function f is the gradient of f dotted with that unit vector. I'm not going to prove it, but you could prove it, and you use limits, use definition of partial derivatives with limits, and you show that this actually works. So you could look this up in the textbook or online or however, and you can see a proof of this. But it should be somewhat convincing that the directional derivative of f in the direction of a vector is always equal to grad of f dot that vector. Let's look at some properties of the gradient. So what I have here is a topo map, and this is one of the most beautiful places in the world. Of course, I'm a little biased because I live real close to it, and that is Emerald Bay, and there's some great hiking around there. The question is, if we look at the function of two variables, the two variables now are going to just be the latitude and longitude, and the function will give you the elevation, then what is the gradient? And if you have a level curve, the gradient is quite nice. What the gradient does is always in the direction of maximum steepness. So that tells you that if you take one step in the direction of the gradient, you will always be walking in the steepest possible slope you can walk. And that is steepest upwards, by the way. Also, the gradient of f is orthogonal to the level curve of the function at that point. So here's the level curve, and if you walk in a perpendicular direction to that level curve, then you will be walking along the gradient direction. So that's really nice and really important and useful in all kinds of ways. One thing it'll tell you, for example, what direction water is likely to flow. It tends to flow in the steepest direction. It tells you what the temperature might look like, or all kinds of different things. In terms of knowing the gradient of f is in the direction of maximal steepness, that is because the directional derivative of a function, if you remember, is equal to the gradient of that function dotted with the unit vector. And the dot product of two vectors is the product of their magnitude times the cosine of the angle between them. But the cosine of an angle is maximal when that angle is 0. And angles are 0 when the two directions are parallel to each other. So that tells us that gradient is in the direction of maximal steepness because it is the direction at which the directional derivative is the largest. Now let's see about finding the gradient. So here's an example. Let's let f of xy equal e to the x plus 2y times the cosine of y. Let's find the gradient of f of xy. So to do that, we find the two partial derivatives. F sub x, the partial derivative of f with respect to x, is equal to, now we take a derivative. Notice we can use a chain rule. The derivative of x plus 2y with respect to x is 1. The derivative of the exponential is itself. So we just get 1 times e to the x plus 2y. And then cosine y is a constant, so you just multiply by that constant, cosine y. For the derivative with respect to y, now we have to use a chain rule. The derivative of x plus 2y is 2 if it's respect to y. There's my 2. Times the derivative of the exponential, that's the exponential, e to the x plus 2y, times the second, which is the cosine of y. I'm using the product rule to find this derivative because we have a product of an exponential and a cosine, and they both have y's in them. So I take the derivative of the first times the second, and then plus the derivative of the second. The derivative of the cosine of y is negative, so that's why it's a minus, times the sine of y, and then times the first. So now we can put this together and then get the gradient. The gradient of f is equal to the vector e to the x plus 2y times the cosine of y. That's the partial derivative with respect to x, comma, 2e to the x plus 2y times the cosine of y minus e to the x plus 2y times the sine of y. A lot of times you're interested in the gradient of a point. So let's find the gradient of f at the point 1, comma 0. And that just means plug in 1 for x, and plug in 0 for y. So notice that e to the 1 plus 2 times 0 is e to the 1, which is just e. Cosine of 0 is 1. So we get e times 1, which is e. So the first component is e. For the second component, we get 2 times e. Remember, we're plugging in the same values. Times the cosine of 0, and that's 1. You just get 2e. And then minus, well, the sine of 0 is 0, so it goes away. So you just get 2e. So we could say that the gradient of f at the point 1, comma 0 is equal to the vector e, comma 2e. So that's how you find the gradient. You just find the partial derivatives. And then if you need to, you plug in the numbers after. This is an example where you only have 2 variables. But if you had 3 or more, it's the same idea. For the gradient, instead of just the partial derivative with respect to x and the partial derivative with respect to y, you keep going and you take more partial derivatives in order. So here's an example, nice little application. So it's predicting the wind direction. So let's suppose a barometric pressure today is P of xy equals the sine of x plus the natural log of x plus 2y. The question is, find the direction of the wind at the point 0, 3. Let me give you a little bit of meteorology. And what that is that wind is caused by a change in pressure. So wind always goes from high pressure to low pressure in the direction of the maximal change in pressure. So it turns out it's going to be the negative of the gradient because the gradient goes from low to high and wind goes from high to low. And in fact, that's why, if you've ever noticed, if you're in one weather pattern today, and tomorrow we're going to have a different weather pattern. So maybe we're going from a high pressure system to a low pressure system. So it's a change in barometric pressure that we're going to end up with maybe rain tomorrow because that's what happens. You'll notice that when you have that change in pressure system, you have a windy day. And that's because you have a high gradient, it turns out. So let's find the gradient. So to find the gradient, we take the partial derivatives. The derivative of the sine of x is cosine of x. The derivative of natural log of x plus 2y, use a chain rule. The derivative of x plus 2y is 1. The derivative of natural log is 1 over x plus 2y. For the partial derivative with respect to x, we just get cosine of x plus 1 over x plus 2y. For the partial derivative with respect to y, sine of x goes away, gives you a 0 derivative. And then we use a chain rule. The derivative of x plus 2y with respect to y is 2. And then the log tells you bring it downstairs. So we get the derivative with respect to y is 2 over x plus 2y. And there's our gradient. We want to plug in the point 0, 3. So we do that. The cosine of 0 is 1. And we have 1 over 0 plus 2 times 3, which is 1 over 6. So we get 1 plus a 6, which is 7/6. Similarly, we get 2 over 0 plus 6, which is 2/6, or 1/3. What we really want is we want the direction of the wind. Let's make that a unit vector. So to do that, I'm going to multiply everything by 6, and we get 7, 2. And then find the magnitude of 7, 2. 7 squared is 49. 2 squared is 4. 49 plus 4 is 53. So we get 7 over root 53, comma 2 over root 53. Now that's the gradient, so now that tells us that the wind direction, which is the opposite direction of the gradient, will be negative 7 over root 53, comma negative 2 over root 53. And there's our wind direction. Now let's talk about tangent planes. Tangent planes, as I mentioned, are really important. And in fact, in the old days, they thought the Earth was flat. Basically, they were looking at a tangent plane. They didn't have a satellite to go out and look and see this big spherical Earth, so they just saw the plane. We want to find out what is the equation of the tangent plane to a surface at a point. Let me remind you that in general, to find the equation of a plane with normal vector v and point x naught, we take v dotted with x minus x naught as a vector, and we set that equal to 0. So remember, v is a normal vector to the plane, and x as a vector is x comma y comma z, and x naught as a vector corresponds to a point on a plane written in vector form. So here's the big definition. And what it says is that if f of x, y, z is equal to 0, is a differentiable surface at a point x naught, then the tangent plane has normal vector n equal to the gradient of f at that point. That is going to make all the difference for us, because in order to find the equation of a plane, you need a point and you need a normal vector. The point is almost always given, and the normal vector is the gradient. So here's a picture of what's going on. This is a surface. I like to think of a surface as a quilt blowing in the wind. So if we look at one little parallelogram of that quilt, it's a parallelogram because it's blowing in the wind. Then if we point directly outward, that will be in the direction of the gradient of f, and that is the normal vector to that surface. So let's look at an example of finding the equation of a tangent plane. So the question states, find the equation of the tangent plane to the surface f of xyz is equal to 2x plus yz squared minus 8 equals 0 at the point 3, 2, 1. We need to find the point, and we need to find a normal vector. The point is just 3, 2, 1. For the normal vector, we use the big definition, which says the normal vector is the gradient. The gradient of this function is the vector of partial derivatives. So the partial derivative with respect to x is just 2, because 2x appears here, nowhere else is there an x. So we get 2. The partial derivative with respect to y is z squared, and the partial derivative with respect to z is 2yz. If we plug in 3, 2, 1, then fx is still 2. There's no variable there, so it's just 2. Fy is z squared, that's 1 squared, which is 1. And fz is 2 times y times z, or 2 times 2 times 1, which is 4. And the gradient is normal to the tangent plane. So the normal vector is this vector 2, 1, 4. So now that we have the normal vector 2, 1, 4, and the point 3, 2, 1, we can find the equation of the tangent plane. And we could say that the vector 2, 1, 4, the normal vector, dotted with x minus 3, y minus 2, z minus 1 is equal to 0. And now let's take the dot product. Notice we're going to get a 2x plus y plus 4z And then 2 times negative 3 is negative 6. 1 times negative 2 is negative 2. And 4 times negative 1 is negative 4. Negative 6 plus negative 2 plus negative 4 is negative 12. I add 12 to both sides, and I get 2x plus y plus 4z equals 12. And that is the equation of the tangent plane to this surface at the point 3, 2, 1. And that's all there is to it. Let's do one more example that's going to look a little different, and that is the following. Find the equation of the tangent plane to the surface. Z equals x squared plus e to the 3y at the point 2, 0. Now this looks a little different because now we have a function of two variables, and our point just has x and y. So the trick on this is you just change this to a function of three variables and make it a point x, y, z. So in particular, we can subtract z from both sides of the equation, and we can get x squared e to the 3y minus z equals 0. Now we have the form that we want. If we take the gradient, meaning finding the three partial derivatives, we have f sub x is 2x e to the 3y, and then it's minus 0, so 2x e to the 3y. F sub y is going to be, the chain rule says the derivative of 3y is 3. So you get 3x squared, the derivative of e is just the exponential, times e to the 3y, and then minus 0. And f sub z is just 0 minus 1, or negative 1. Now let's plug in the point 2, 0. If I do that, we get 2 times 2 is 4, times e to the 0, and that just gives us 4. We get 3 times 2 squared is 3 times 4 is 12, times e to the 0, and that just gives us 12. And then for the third component was just negative 1. So there's our normal vector. Now the point, we have a little more to do because we're only given 2, 0, but it's no big deal because z is equal to x squared times e to the 3y. So we get 2 squared times e to the 0, which is just 4. So we could say that the vector x naught is 2, 0, 4. So now let's just put this all together. And we get the normal vector 4, 12, negative 1, dotted with the x vector minus the point vector. So x minus 2, y minus 0, z minus 4 is equal to 0. And now the rest is pretty basic. We just take the dot product. So we get 4x plus 12y minus 1z. So that's 4x plus 12y minus z. And now let's do the arithmetic of the dot product. We get 4 times negative 2 is negative 8. We get 12 times 0 is 0. And we get negative 1 times negative 4 is positive 4. So negative 8 plus 0 plus 4 is negative 4. We add 4 to both sides, so we get 4x plus 12y minus z is equal to 4. And that's all there is to it. So that's all I have today to talk about the gradient vector and tangent planes. If you have any questions, please let me know. I'm happy to help. Or if you have another instructor, please ask your other instructor, and I'm sure your other instructor will be very happy to help also. So until next week, have a great week. Make sure you study and practice and practice and practice so you can get good at this. And next week, we'll have a new topic. So have a wonderful week.